Okay, so for your assignment this week, you guys are basically solving word problems of systems of equations. And the hardest part is not necessarily the solving, but it's the modeling, the coming up with the equations. That's the hardest part. So I've got a few examples here, and I'm going to go through how you come up with the equations for these type of problems. And it should give you a good idea that you can see kind of the three different types of problems that you can use. There's, the systems kind of, there's different categories that problems fall into where they're kind of set up the same way but with different numbers. And so we'll see the different types of setups that there are, and that should help you with the assignment. So mathematical model. So a mathematical model is a description of a situation, and we usually do this using equations. So you're going to have your variables for your unknowns. You're basically, a mathematical model is trying to take what's going on and turn it into one or more math equations that then you can go and solve. So the basic steps is first figuring out what are you trying to find. Those are your unknown values. Those are what you're going to set your variables as. And what is the information given? You can do those in either order, but you need to figure out what do you know and what do you not know. Then draw a picture if necessary. Sometimes problems are really, they lend themselves to pictures. If you're doing anything involving distance, I tend to draw pictures for things like that, or any kind of physical, thing. Sometimes pictures are really helpful. Sometimes you don't really need a picture. Sometimes you want to put something in a table, but you want to try to organize the information so that it's a lot easier to figure out how things are related. Once you've gone through that, that's when you need to write the equation or multiple equations. If we're using systems, that means there's going to be two or more equations. And you want to, in order to solve a problem, you need as many equations as there are unknown variables. So if there are three things you're looking for, three unknowns, you need to write three equations. If you don't have enough equations, you can't actually solve the problem. So you need to make sure that you have the same number of equations as you do unknowns so that you can actually solve it. And then once you have your system set up, that's when you solve the equation or you solve the system to actually get your answers. And then you need to just do a sanity check to make sure that your answer makes sense and it's reasonable. Because if it's not, like if you are solving for price of something or the quantity of something and you end up with a negative, that doesn't make sense. And so that is an indicator that somewhere along the way you have a mistake. Either the mistake is in your solving or the mistake is in your equation or your system. So you always want to kind of check, does my answer make sense before you say, okay, I'm done. So I've got 4 examples here, and I'm not going to go through the solving process of these because there are videos on how to solve systems. I'm focusing on the modeling process, how you actually write the equations for each of these. So this example is a chemistry example, but this is like the first category that you often see systems, and that's where you're counting the numbers of things. So this category is counting how many you have. It's not an official name, that's just the category I stick it into in my brain. So this is related to chemistry. We have weights of atoms and molecules are measured in atomic mass units, which is abbreviated U. Now, way back when I took chemistry, it's AMU. Apparently, they changed the symbol for this. I found that out when I was researching. So a molecule of CH4, which is methane, is made up of 1 carbon atom and 4 hydrogen atoms, and it weighs 16.043 atomic mass units. A molecule of 6,3H8, which is propane, is made up of 3 carbon atoms and 8 hydrogen atoms and weighs 44.097 U. Find the weights of a carbon atom and a hydrogen atom. So our goal is we want to find the weight of carbon and the weight of hydrogen. So those are going to be our unknowns. That's what you want to set your variables at. So whenever you're doing a modeling problem, you always want to be explicit and tell me and tell whoever is looking at your work what your variables are and what they mean. Because you can make up any variable, you can use any letter you want, and if it's not given to you, you need to specify what they are. So I'm going to say that C is the weight of carbon, because C makes sense for carbon. And then let's use H for hydrogen. So H will be the weight of hydrogen. So it's good to just start out with your things that you're looking for. We're finding the weights of both of those and setting your variables so that way you know what these letters mean and what you actually found in the end. It's all about communicating. So now I have my variables, and now I have to figure out what I know. And I said that this is a counting problem because we know how many we have of each of these things. So if I look at the CH4, the methane, I have 1 carbon atom and 4 hydrogen atoms. So when I write my system, I have 1 carbon and 4 hydrogen. So you're basically adding those things together. You're adding how many molecules you have. And if we have 1 carbon atom, we multiply by the weight, that's going to be the total weight of our carbon. So 4 hydrogen atoms times the weight of the hydrogen atom will give us the total weight of hydrogen. So we have here the total weight of the carbon plus the total weight of the hydrogen. So that those added together need to give us the total for the whole molecule. So that's going to equal 16.043. Your second equation is going to be for the propane, and it's going to be very similar. You're literally just counting how many you have of each thing and setting it equal to the total weight. So we have 3 carbon plus 8 hydrogen, and that weighed 44.097. Now to finish it up, in order to make this a system, you have to use your curly braces, because that is putting it together and saying, okay, these are my equations that I'm using for this system. If you don't have a curly brace, it's not clear that these are your final equations, that this is your system. This could be you, because sometimes you come up with side equations as you're trying to figure things out. The curly braces, they indicate that these are taken together. These are my equations for the system. So I'm going to highlight this. This is the final system. So making that very clear. Every time you have a word problem, you have to give the system before you do anything. You need to make it clear, what are you solving? What are the equations that you're solving? So that is the system, and this is for any problem where you're counting how many of something you have. Like, for example, there are the types of problems where you went out and you purchased, let's say, 5 apples and 4 oranges, and then you get a total cost. Those fit into these categories where you're counting how many you have of something, and then you have a total cost, a total weight, you're given some sort of total. Those fall into this category. They're set up all the same, you just have different variables, or your right side might be weight, it might be price, but it's going to be some total. Now, I'm not going to go through and solve this, but I am going to give you the answers for the solving, so that way you can practice this on your own to solve this system. And then you can check your answers with what you are supposed to get. So if you go and solve the solution to this particular equation, you will end up with C equal to 12.011 atomic mass units, and then H is 1.008 atomic mass units. So when you solve, those are the numbers you should get. And if you don't get that when you solve this on your own, then there's probably an error somewhere in your math, maybe the method you used. I would solve this system with elimination because all I would need to do is multiply the first equation by either a -3 to get rid of C or a -2 to get rid of H, and then that will make it pretty easy to solve. But you can also use substitution if you just solve that first equation for C and plug it into the second. So this system is fairly easy to solve either way. It's just a matter of personal preference there. So that is your solution, and when you when you solve a problem like this, you should give your final answer in a sentence. So you would say, the weight of a carbon atom is 12.011 atomic mass units, and the weight of a hydrogen atom is 1.008 atomic mass units. So you're basically taking that final sentence and kind of rewording that sentence with your answers, basically. That's how you would answer a word problem, so that it's clear what your actual answers are. So are there any questions on this first example, maybe how I came up with the system, anything related to this first example? Okay, yeah, I started with the most straightforward problem. Okay, so example 2. So here we're going to look at the cost of things. And cost is another very common type of problem where you're basically trying to come up with how much something costs. Now this one is a twist on the most common, because usually they'll do, okay, the price of this plus the price of this, and you're trying to find how many. This is kind of going in the other direction where you know how many are, and then you're trying to find the price. So it's slightly different than a typical cost, but you're still kind of, you're grouping these things together, you're adding things together. You'll see that there's sort of a pattern to how each of these are set up. So connecting a Blu-ray player to a television set these days requires an HDMI cord. You bought a 6-foot cable off of Amazon for $6.99 and a 3-foot cable for $5.94. I actually went on Amazon and found these prices, so these are accurate as of this morning. Assuming that the cost of a cable is the sum of the cost of the 2 connectors and the cost of the cable itself, what is the cost of a 4-foot cable? So we want to know the cost of a 4-foot cable. But in order to find the cost of the 4-foot cable, you need to first find the cost of the connectors and the cable itself. So those are our real unknowns. There's the cost of a connector and then the cost of the cable. Usually I would use C, but C for connector and cable that's way too confusing. Now, if we're looking at the cable, they're giving us different lengths. So I'm going to use L for the cable, and I'm going to say L is the length of a cable because we're getting a 6-foot cable and a 3-foot cable. So we'll use L for length since those are different lengths. I'm going to say L is, and it's not exactly going to be the length because we know the lengths, but we don't know what's the cost of that cable. So it's the cost of, and let's just say 1 foot of cable. The most basic length here because our units are in feet. And then I can use C for the cost of a connector then. So I've got my units. And now this is going to be very similar to the counting problem, but it's got a little twist. So I've got a 6-foot cable, and then we know the 6-foot cable has 2 connectors. So when I write this system, I'm going to have 2 connectors. That's going to be 2 times the cost of a connector. And then I'm adding in the cost of the 6 feet of cable. So since I made the cost of 1 foot of cable L, then I have to multiply that by 6. So that's going to be 6L. And so this is going to then give me the total cost of that 6-foot cable, which is $6.99. Now the other cable, we have a 3-foot cable. That also has 2 connectors, so that part's exactly the same, but the difference is now it's 3 times L. And that is $5.94. So I've got two variables, two equations. So that means I have my system, and so I then add my little brace to indicate that this is my system that I'm solving. So you would have your system. This system is very easy to solve with like elimination, because you've got 2c and 2c. All you would need to do is change the signs in one of the equations to add them together. So this one's super easy to do with elimination. Now, when you solve, you're going to end up, as for the cost of the connector, it's 2.445 exactly. We can round that to 2.45 if you want. And then the cost of the length for each foot ends up being 35 cents. So most of the bulk, the cost, is in the connector and not the cable itself. Now what happens is a lot of people will, okay, they do that and they're done. They're like, I have found my system. But that is not what the question is asking. Because the question is saying, what is the cost of a 4-foot cable? So you need to actually take those answers and actually answer the question. So you would have to say, okay, a 4-foot cable has 2 connectors. So that's 2 times the 2.445 plus 4 feet, and it's 35 cents per foot. So you would actually have to do an additional mathematics there to actually answer the question. So it's always good to make sure you are answering the question that's asked, because that's where a lot of people miss things, is they just go and they solve and they think they're done and they're not. So this, when you do that, that comes out to $6.29. And so then you would have to write this in a sentence. You would say the cost of a 4-foot cable is $6.29. Do you have any questions? Okay. Now, example 3. Now this is going to be just like the last problem, problem 5 on your assignment this week. The numbers are different, and I'm not doing all 3 parts of that problem, but it's going to be enough to get you started. So the third type of problem that you often see when you're solving systems involves mixtures. So this is another type where you're having mixtures. Usually you have percents involved when you're doing something like this. And like the problem on gasoline is one of these types of problems, because you have octane, and that's actually basically what percent, it's a mixture basically. So you're going to be doing it very similar to this, where you're dealing with things and you have percentages of things. So this is like the next type of problem that you see. So a chemist needs 10 liters of a 33% acid solution. Now I did try to find like a real situation, like if it was going to be hydrochloric acid and how much percentage you need. I'm not a chemistry major, and I spent some time looking for chem labs trying to figure out like an actual problem that you might do in chemistry. And then I decided, you know what, as long as you have the general idea, I'll just make up numbers, because I really need to find an actual chemist to help me here to get a real problem. But I did try to find like real situations for everything here. So a chemist needs 10 liters of a 33% acid solution. The solution is to be mixed from 3 solutions whose concentrations are 12%, 18%, and 100%. 100% is basically pure acid. How many liters of each solution do you need to use as, apparently I accidentally typed a word in between there when I was typing, as little as possible of the pure acid. So you want as little as possible of the 100%. That's 100% acid. So it says we want to know how many liters of each solution. And we have 3 solutions, so we're going to have 3 variables. And I'm going to just use X, Y, and Z because it's not really, there's 12, 18, 100%. There's not any good variables that kind of make sense there. So let's, X is liters of the 12%. Y is liters of 18%. And then Z is liters of, oops, why did I add an extra t there? Liters of 100% acid. So I have to make sure I know which percent goes with each variable here. So we have 3 variables. We need to have 3 equations in order to solve this problem. So the first thing is, when you're doing a situation like this and you type a system that's involving mixtures, is one of your equations is always for the total amount that you have, like the total amount of liquid or pounds or whatever you have, the total amount. So our total, we need 10 liters. So we're going to take the liters of X plus the liters of Y plus the liters of Z, and that needs to equal 10 liters. We need 10 liters total. The second equation in an example like this always utilizes the percents. You basically take your total equation and multiply it by the percents. So that'd be 0.12 for X plus 0.12 of Y plus 1 Z, and then we need 30% acid, 33% acid, so I need to multiply that 10 by the 0.33. So for mixtures, anything with percentages, the first equation is the total, the second one involves the percents. Now we need 3 equations here. We have only 2, so this is not enough to solve the problem. But we want to know how many liters of each solution do we need to use as little as possible of the pure acid. So we need to think about what's going on. If you are trying to use pure acid, you add anything that's less than pure, you're going to dilute the system. And the thing that's going to dilute it the most is the 12%, because the 12% has more water and less acid than anything else. So as you add 12%, you're adding in more water than, say, the 18% adds in. So that's going to dilute it the most because it has the least amount of acid. So if you want to use as little as possible the pure acid, you don't want to dilute it. So you want to not use what would dilute it the most, and the 12% would dilute it the most. So you don't want to use the 12% because that's just going to dilute it too much. So you really want to use the 18% and the 100%. So to use as little as possible the pure acid, we don't want any of the 12% in this case. So your third equation would be that X is equal to 0. And so that is now your third equation. And that now gives you your system that you can solve, and then it will break down to a system with 2 variables. And so then you can find out, well, how much of the 18% and how much of the 100%. There are other types of equations where they tell you, okay, you're going to use 2% of, say, the 12%, and then you can figure out how much you need of the other 2, or not 2%, 2 liters. So usually you're going to be given some sort of amount. If it's a 3 variable system like this, they're going to tell you you need this much of X, or maybe this much of Y, or so forth. So for this particular problem, when you go on to solve it, you will of course get 0 liters of the 12%. You will come out, and this is rounded to 8.17 liters of the 18%. And a 1.83, again, that's rounded, of the pure acid, the 100%, when you go to solve that system. So when the question says how many liters of each solution, you need to make sure you're using 0% of 12, 8.17 of 18%, and 1.83 of the 100%. So you need to make sure that you're specifying how many liters of each, not just liters of 2 of them, but all 3 of them. Any questions? Yes. Yeah. So when you solve this, you will end up having 2 equations because you're already given one of the variables. Your system still sets up with 3 because you start with 3 unknowns, but then 1's solved for you already. So then you're solving with 2. All right, so next one, this is another mixture problem, but this one is involving parts of things. And this is probably the most difficult one to set up. And this is another category where you're given, you're trying to find, you're given how many parts something has, and you're trying to find the amount, how many pounds, liters, or something like that. But you're not given a percent, you're giving parts. And parts means you have to put these into fractions, and you have to think about how many parts you have total. So if you have like 2 parts plus 3 parts, that's 5 parts total. So you're using fractions rather than percents. So it's sort of set up similar to the percents, but it's a little more work because you have to think about your parts. This is going to be a lot like question 4 on the assignment, which also is involving fertilizer. This one, I actually did some research to find out what kind of fertilizer is used out there. I was actually trying to find some example mixtures. I didn't find an exact thing, so I just tried to do some modifications, but I did find out kind of some chemicals that are used. Actually, I have the source at the bottom. There was actually an article about mixing pesticides together, so I thought that was interesting. So farmers usually mix pesticides together before spraying on their crops, and a study on honeybees, that's the one linked below, found that the pollen in a hive contained on average 7 different pesticides. So they're doing a lot of different mixtures in their, their crops or whatever. They're not just doing 1 or 2 pesticides. Obviously, we're not going to use 7 because that would be 7 different variables, and that would be a mess. So we're just going to look at 3 variables. We're going to just use 3 pesticides. So a mixture of 3 gallons of fluvalinite, that was one of them that was found in the study. 8 gallons of coumaphos, that was another one in the study. And then 2 gallons of chlorpyrifos. That's a third one that was in that study. So these are actual pesticides that were used. It is required to kill a destructive crop insect. Now, commercial spray X, I tried to find actual pesticides out there with these chemicals. I could not find that on the internet easily, so that's why I just used an X, Y, and Z. I could not actually find brand names that had this particular mix. Commercial spray X contains 1 part fluvalinate, 4 parts coumaphos. Commercial spray Y contains only chlorpyrifos, and commercial spray Z contains all 3 chemicals in equal amounts. How many gallons of each type of commercial spray gives the desired mixture? Okay, so let's look at what we need to know. We need to know how many gallons of each spray. So we're not looking at the gallons of pesticides, we're looking at gallons of spray. So since these sprays are labeled X, Y, and Z, that would make sense. So our unknowns, X would be gallons of spray X, Y would be gallons of spray Y, and then Z is gallons of spray Z. We know how many gallons we need of each chemical, but we don't know how many gallons of each actual pesticide mix to put in. So that's what we're looking for. We're looking for how much do I need of X, how much do I need of Y, how much do I need of Z. So those are our unknowns. So when we're doing something with parts, we need to think of how many parts we have. So I'm going to actually go to a new slide because this was a wordy problem here. So our mixture, I'm going to look at what we have for our chemicals. So we have fluvalinate as 1 chemical. The second chemical was coumaphos, and the third chemical was chlorpyrifos. And I need 3 gallons of the fluvalinate, 8 gallons of coumaphos, and 2 gallons of chlorpyrifos. So I know how many totals that I need of each. So those are going to be my totals. So my equations are going to be equal to those numbers. And I need to figure out, I need to know how much of X, how much of Y, and how much of Z I have to mix together. So X, I go back to my other slide, it said X contains 1 part fluvalinate and 4 parts coumaphos. So 1 part and 4 parts. So I'm just going to kind of list. So X is made up of 2 of those chemicals. Y contains only chlorpyrifos. So I'm just going to say it has 1 part of chlorpyrifos and it has nothing of anything else. And then, go back. For Z, Z contains all 3 chemicals in equal amounts. So we can say 1 part of each. So we have 1 part of fluvalinate, make that actually look like a U. 1 part of coumaphos, 1 part chlorpyrifos. So I've written down how many parts we have, but we have to look at these in terms of fractions, so we need to know how many total parts we have. So for X, that gives us 5 parts total. For Y, we have 1 part total, and then Z, we have 3 parts total. So when we convert these into fractions, I'm going to have to divide each of these by the number of parts in order to get a fraction, because it's 1 part out of 5. So I'm going to go back to my system, and I'm going to just, I know each of these are going to be equal to the total number of gallons. So I can have those on the left, I can put them on the right, it really doesn't matter. So let's look at we're going to do an equation for each chemical. So our first equation is the fluvalinate. So we're going to need 3 gallons total. And for chemical X or brand X or whatever, it's 1 part out of 5. So 1/5 of it is X. Y doesn't have anything. So I'm not even going to list Y, because Y doesn't have any of that chemical. And the spray Z has 1 out of 3 parts. So that's going to be 1/3 Z. So 1/3 of that spray contains fluvalinate. Now I'm going to look at the second chemical, coumaphos. And again, I'm going to look at fractions. So the spray X, 4 out of 5 parts contains that chemical. So that's going to be 4/5 X. Y doesn't contain any of that chemical. And Z is equal parts. So that's going to be 1/3 Z. 1/3 of however many gallons we use there contains coumaphos. Our last one is chlorpyrifos. And so we need 2 gallons total. The spray X doesn't contain any of that, so I don't have to write that down. I do have that chemical in Y. Y is only chlorpyrifos, so that's just 1 part out of 1, which is 1. And then spray Z also contains chlorpyrifos, and that's 1/3 of it. So 1/3 of Z has that chemical. So now I've got an equation for each chemical, and it's telling us how much of each spray contains that chemical. And so that is going to give us our system. So now we have a system of equations that we can solve. We have 3 equations, 3 unknowns, and then you have to go about and solve this to figure out how many actual gallons of each you would need. So when you solve this system, you end up with 25/3, or 8 1/3 gallons of spray X would be needed in order to get our mixture. Then we have 2/3 of a gallon of Y, and then you need to mix in 4 gallons of Z. in order to get your total amount of the chemical. So if you add 8 3/3 plus 2 3/3 plus 4, 8 1/3 plus 2 3/3 gives you 9. 9 plus 4 is 13. So that adds up to 13 gallons total. And when you're looking back at how many gallons we needed of the chemicals, we had 3 gallons plus 8 gallons plus 2 gallons, that's 13 gallons. So we are getting 13 gallons, and if you mix this many gallons of each type of pesticide, that will get you the correct number of gallons for each of the particular pesticides you need. So I guess I should say if you add up 8 1/3 gallons, 2 3/3, and 4 gallons of the sprays, you'll get the correct proportions of the chemicals that you want in your pesticides or your mixture to spray. Do you have any questions? If you try to set up, if there's any problem that you're given where it's involving parts, try to set it up this way, and that will help you. Because if you set it up this way and then think about how many parts you have and try to convert them to fractions, then that will aid you in coming up with the equations. Yeah, if you use this one as a guideline, you should be able to get it. The most common issue people have is the solving part. That's usually where errors occur. Errors don't usually occur in the setup, it's in trying to solve and then not getting your right answer. So when you go back and solve, you should make sure that however many gallons you got correctly adds up to the total that you need, because that's a good check to make sure that you've done it correctly. Because if my final answer is added up to 15 gallons and I'm only supposed to have 13 gallons, that tells me I messed up somewhere. So that's a good check. So those are the different types of problems that you can see when solving systems, and pretty much every type of system is some variation on one of these 4 types. So if you recognize that, okay, this is an accounting type, or this one's involving money, or this one's involving percentages or parts, that should help you going forward and working on any kind of systems that you would need to solve. So do you have any other, any general questions for me that I can answer? Question 1 on the assignment. So question 1 on the assignment is actually, you're basically creating 2 linear equations, and those are going to be your system. So you're going to have an equation for the first salary situation, equation for the second one. So you're going to have like a y equals, or whatever variables you use. And so your system is then composed of your 2 linear equations. And then that is how you solve. So you're going to have like your total, your base salary, your base amount, plus the percentages of sales, essentially. Yeah. So so if you're doing anything where you're getting some percentage of something, and then you have a base pay, that's always going to be like a linear equation. And then it's fairly simple once you recognize that. So that's it. So thank you very much for showing up and asking questions. I was not sure if this time was going to be good, because I think there's still only like 9 people in our course who have actually filled out the survey. And so I was like, well, I'll try lunchtime, we'll see what happens. But thank you for showing up and asking questions. Really do appreciate it. I'm glad that this is what you needed. I know that this is where most people don't struggle necessarily in the solving part. It's the setting up part. So knew that this would be very helpful. So I'll try to get this video out by this afternoon, so that way you can also have access to like the PowerPoint and everything to look over later. So I think I'm gonna go grab some food, and hey, thank you so much. I hope you have a great Friday and a wonderful weekend. And hopefully I'll see you at the next one. Bye.